Hey class, Adam Ward here. I want to talk to you today about feed-forward systems. And this lecture goes along with Chapter 5, or what Chopper calls Lecture 5 in your textbook. And so when we think about feed-forward systems, what we're trying to answer is the question, how is a downstream water body impacted by processes that are happening upstream in the system? So in the example of the Great Lakes, where we've got Superior and Michigan flowing together into Huron, Erie, Ontario, and so on, right, it's easy to imagine that extensive pollution in Lake Michigan must have some impact on Lake Huron, Erie, Ontario, and down through the chain. The question is how? Up until now in class, we've dealt with a single CSTR, and so today we're going to investigate multiple CSTRs that are configured into a more complicated system. One thing to point out here for you, Lake St. Clair is down in between Huron and Erie. That'll come up in your homework, so I wanted to make sure that folks knew where that was and how it fit into the system. So let's look at what I think is our simplest case for lakes in series, two CSTRs. And so what you can see I've drawn here are two well-mixed systems, each that has a load, W1 and W2, a concentration, a volume, and a first-order reaction, K1 and K2. You'll notice that now that they're connected, I've labeled the discharges between them Q12 and Q23, assuming that moves on to some future CSTR. Now, for either one of these two CSTRs, at this point in the class, you should be comfortable writing out the general equation. So the accumulation of mass in the system, or the time rate of change of mass in the system on the left-hand side, is equal to the loads minus the outflows, or the sinks. For Lake 1, we've written this out. Lake 2 looks very, very similar. Importantly, the feed-forward system comes when the outflow from one becomes the inflow to the next. So I've highlighted this in red for you. Mass that is leaving 1 with this term minus Q12C1 becomes an inflow to Lake 2 in the system. And so now mathematically we've coupled these two equations together, right? As goes CSTR number 1, goes the load that is received by CSTR 2. So this is what we mean by feed-forward systems. The upstream lake affects the downstream lake. I want to talk through what Chopper calls the cascade model. This is a special case for two reasons. One is that we're going to assume that these four CSTRs are all at steady state. And the second being that we've got some critical assumptions. We'll assume that they all have the same reaction rate, they all have the same discharge, they all have the same volume. So these are identical CSTRs. So if we go through and write out the mass balance for each lake, we would start with the accumulation term, but of course it's at steady state, so dc dt is equal to 0. There is no concentration change at steady state. And so we've got 0 equals terms that describe inflows, outflows, and reactions. And if you like, you can solve that equation to explicitly represent C1 as a function of C0, and then Q over lambda. For Lake 2, I'm writing out the exact same information at this point. And so C2 becomes a function of C1. Again, that's what makes it a feed-forward system. And what you can do is plug your solution for the first equation into the second equation. And you get what I've written along the bottom of the screen here in blue. Now I can solve for the concentration in 2 as a function of the system characteristics and the upstream value. And so we get C2 is equal to that term in parentheses now squared times C0. Why squared? We've been through two lakes. We can generalize this cascade model as follows. In the nth lake, the concentration can be expressed as the quantity of Q over Q plus KV to the N times that upstream condition. Okay, why would we do this, right? Why break the system down? Well, if we've got just one CSTR, all we could say is that in space this is the concentration. But as we increase our resolution by having 2 or even 4 CSTRs, we start to gain some process understanding of how multiple lakes or multiple reaches of a river, if you want to think of these as a river, act on and then transfer pollution to the next downstream element. So when we start to put many CSTRs in series, we can describe things like chains of lakes. So imagine that as Superior, Huron, Erie, and Ontario, as I've written across the top of the screen now. And where we'll be going with this in the future is to describe rivers and streams as nothing more than a series of CSTRs that are incredibly small and stacked one right after the next. So that's what we can do with our cascade models. A little bit more generally, what can we do about systems of CSTRs if we can't make steady state assumptions, or even if we can't make assumptions that things are uniform? So on the top of the screen here, I'm showing you what you already know from previous lectures, the mass balance equation for one CSTR, and the general solution, meaning the loading or the W term is equal to 0, simplifies down to the equation on the right. Now that we've got multiple systems, we're going to establish some new terminology. So not just having these lambdas anymore, but these lambdas will have some subscripts with them. So a lambda 2,1, for example, is representing the effect of a load into 1 on the concentration in 2. Or maybe you like to think of it sort of right to left here. How does the concentration in 2 change as a function of loads into 1? So now we have lambdas that will link these terms together. Let me show you where those lambdas come from. 2 CSTRs, 2 mass balance equations, and we could simplify those out to this point. Now, if you're not clear where those come from, I would encourage you to write the full mass balance out for each lake, as we did along the top of the screen there, the V dc dt equals W and so on, and simplify that down in group terms until you can formulate this equation. Now, where do these terms come from? These come from having simplified down the lambdas for each lake, and those look as they did before, Q over V plus K. That's how the lake acts on a load into itself. How does 1 act on a load into 1? How does 2 act into a load on 2? The thing that we're newly introducing here is this lambda 2,1 term. Right? And this lambda 2,1 term describes how loads into 1 are transferred into concentrations in lake 2. And so I'm showing you in blue a little bit of where that came from. The load was Q times C, and as we simplified the algebra, we divided both sides by V2. And so you end up with a term that looks like plus Q12 over V2 times C1, or lambda 2,1 times C1. I've skipped a bunch of algebra in what I'm showing you here. And so again, I really think it's important that you practice going from the top of that slide to those mass balance equations that are written in the bottom left. That's something that I'd like for you to be able to do on your own. Now, those are mass balance equations. Those haven't been particularly useful to us. We're interested in the solutions to these equations. And so for one lake, the first lake in the system, we've done that solution before. And so I've printed it on the slide already. C is equal to C naught E to the minus lambda T. If you look in your textbook, Chopra then provides you solutions for a second, a third, and I believe even a fourth lake in series. Right? And so the farther and farther we move through the cascade of lakes, the more and more complicated these become, because these lakes have some memory of what's happening in previous upstream systems. So, by the time you're done watching this video, you should understand what a feedback system is. You should double check that you are comfortable writing mass balance equations, making simplifications for steady state conditions, and manipulating those mass balances to form equations that have lambdas in them. That'll be a skill that you need to have as we continue to progress through this class. Thanks for sticking with me, folks. You'll see a similar video shortly on feedback equations.